Okay, good morning, everyone. So last time we were talking about the photoelectric effect, which we hope to finish today. And so here's the setup again. So we've got some atom sitting here minding its own business. And we're going to pretend that it's a hydrogen-like atom. That will also be true for the inner shell electron of an atom. And so the energy of it in the initial state is minus the atomic number squared, E squared over twice the Bohr radius. Notice it's negative because it's a bound state. And its wave function is just like for hydrogen, except with a factor of z. So it's z cubed over pi Bohr radius cubed. And then there's an exponential. So again, we're only worried about the case of this thing in its ground state. You could do the excited states, but that would just be more complicated. Okay, and it's minding its own business, and along comes a photon, which I'm drawing the wiggles for the electric field. Those are the electric field directions as it's wiggling up and down. And so that direction, the direction in the plane of which I'm writing, is the polarization direction. And this direction along the direction the wave is going is the wave vector direction. So it's got frequency omega, wave vector is its direction, which we'll later call z hat, but it's times omega over c, because that's true for an electromagnetic wave. And so this photon hits our atom, and then it pops out the electron that we're talking about in some direction, which we're going to call K, capital K. Okay, and the final state wave function is some normalization constant, e to the I capital K vector dot r. And then the final state energy is positive, h bar squared capital K squared over twice the mass of the electron. Okay, and our goal in doing this is to find the differential cross-section for absorption. Okay, so it's going to be something with units of area, and it's something that an experimentalist could measure and compute. Okay, so last time we were mentioning the fact that there's a little bit of a problem with the normalization constant A here for our electron, because there's really no way to normalize this except to put it in a box. Okay, so to make A finite, we put the whole system in a very large box, a light year across maybe. And we'll call the sides of the box L. Okay, and so going back up here, here's our giant box that includes everything, some cube. Okay, and so now we can figure out what the normalization is. Because if we're going to normalize the state to 1 now, that's going to be the integral over the box times the wave function of the final state in magnitude squared. But because this thing is a plane wave, that's just going to be a squared. Okay, and then that's a constant, so this is just going to be the volume of the box, which is L cubed. And so now our normalization constant is a finite number. L to the minus 3 halves. Okay, and so eventually we're going to take the box size to infinity in the limit, but we can't do that right away because the normalization would go to 0. The other thing we're going to do is we're going to impose periodic boundary conditions. And we'll see in a moment why we're allowed to do that. So the allowed values of capital K vector are the ones where when we go from one end of the box to another end of the box, the wave function is the same thing. So that means psi k of r is supposed to equal psi k of r plus L. And now I can actually multiply by any integer times x hat plus any integer times y hat plus any integer times z hat. Right? That's moving to the other side of the box nx times in the x direction and y times in the y direction and z times in the z direction. So as long as those are integers, okay, we should get back the same thing. And so that tells us that the x component of k should be 2 pi over L times the integer n sub x and 2 pi over L n sub y and 2 pi over L n sub z. So now we notice that, okay, if we take L goes to infinity, then basically all the allowed k's are getting very, very close together because the prefactor 2 pi over L is going to 0. And so we recover the continuum limit where all k's are allowed. Okay, so all k's allowed when we take the limit L goes to infinity. And if we're taking L to be 1 light year, we'll never notice the difference between continuous and the discrete things that are very closely spaced. Okay, so that's, so one more thing is we're going to want to check later that the final answer, meaning the cross section, can't depend on L if we've done everything correctly. Because how is the system going to know if we chose our box to be 1 light year across or 2 light years across? It can't possibly care. All right, so now let's recall the formula that we're going to use to do this. And this is equation 16.2.8 in the notes. And that says the differential cross-section for absorption is, there's a bunch of constants. There's 4 pi squared fine structure constant, h bar over mass of the electron squared times the frequency. Then there is a matrix element that we're going to have to compute. And notice I am not assuming the dipole approximation. I'm writing the whole thing here. And then there's a density of states. And here I'm going to write it a little bit more specifically than it is in that formula in the notes, because now we have some information about this particular problem. So the density of states depends on the final state energy. And it also depends on the degeneracy parameters. But in this example, the degeneracy parameters are going to be just the angles of the final state electron. Okay, and so now I need to write a differential for those. Okay, and so what we've done here is we've recognized that in this particular example, these are the degeneracy parameters, which before we were generically calling U. Okay, and the reason they're the degeneracy parameters is that you get the same energy for a plane wave, regardless of which direction the plane wave is propagating. So same energy for a plane wave, regardless of direction. And so there are differentials of them there. And so what we're supposed to do to get the actual cross-section is we're going to integrate over those later. Okay, so from this formula, we have two main tasks now. We have to compute this matrix element, and we have to compute the density of states. Okay, so to me, the density of states is always the harder part. So let's do that first. So need density of states. Okay, and to do that, what we're going to do is consider a volume of K space. And count how many states there are in it. And this is where putting the system in a box helps, because we know there's one state associated with every integer triplet in X and Y and Z. So the volume of K space is dkx, dky, dkz, which we could also call d3 of the vector capital K. Okay, and in that volume, the number of allowed states, these are final states for the electron, is, so there's one for every L over 2 pi, because if we go back up here, right, we recognize that each K came as an integer times 2 pi over L. Okay, and there are 3 of those integers, so we cube this, times d3k, which we can write as, in spherical coordinates, for k, L over 2 pi cubed, k squared dk, d cosine theta of k, which I'm going to call d cosine theta f for final state, because the k direction is the final state direction. And then d phi for these things. Okay, so we're counting the states, but we also know, so we want to relate this to the energy. We also know that if we take the derivative with respect to k of the final state energy, the final state energy is h bar squared k squared over twice the mass of the electron. And so this is equal to h bar squared capital K over m sub e. And so what that means is that capital K squared differential with respect to K is equal to me K over h bar squared differential with respect to energy. Okay, so now we're going to put this equation together with that equation and write it like this. The number of states in a range of differentials. So differential in final state energy, differential in the cosine of the angle of the final state electron, and the differential in the phi direction of the final state electron is equal to L over 2 pi cubed MEK over h bar squared. And then we have our differentials, because the number of states in the range should be proportional to how big the range is for each one of these variables. Okay, and then finally, that gives us the density of states, because if you stare at equation 15.3.16, you realize that's exactly what the definition of the density of states is. So this is rho from equation 15.3.16. Okay, good. So we've done half of what we needed to do. If we go back up to our formula here, we've identified this part. And now we need to work on this part, the matrix element. Okay, so let's just summarize where we are. The absorption differential cross section. So notice I've divided by d cosine theta f and d phi f from the previous formula. This is equal to our constants that we need to keep track of. And then our other constants that have now come from the density of states. And now our matrix element squared. Okay, so the first thing we can do is clean up the constants out front a little bit. So this is equal to 4 pi squared fine structure constant K over ME h bar omega. And then there's a factor of the volume of the box divided by 2 pi cubed. Now, I promised you earlier that this thing wasn't supposed to depend on L. And so that means that when we compute this matrix element, before we even think about it at all, we already know how it should depend on L. It better go like 1 over the square root of L cubed. Because that way, when I square that, that dependence on L will cancel this dependence on L, and everything will be okay. And so we'll know if we made a mistake if it doesn't behave that way. All right, now we'll actually almost immediately see that it does in fact behave like that, because now we're going to write down what the matrix element is. So I'm just writing this for matrix element. Okay, so let's see what we can do first. We can take the fact that the final state is an eigenstate of momentum to just replace this momentum operator by the momentum of the final state. So it's good when things are eigenvalues of things that are next to them. This is the polarization of the wave dotted into now the number, which is the final state electron momentum. Okay, so we've got rid of that operator. And now the rest of it we can evaluate in position space. So we're going to be doing a big integral over the integral in the box. And now we can write down what the wave function of the final state was. This is our factor of A. Okay, and then there's a factor from here, which in position space, e to the ik dot r is just e to the ik dot r, but now it's little k, because that's what was in that exponential. And then finally, there's the wave function of the atom, which is, from our setup, z cubed over pi Bohr radius cubed e to the minus z r over Bohr radius. All right, so now if we stare at this, we see, aha, there's our 1 over square root of L cubed, just as I had predicted a few seconds earlier. And you might say, but wait a minute, we're still integrating over this big box. Won't that give us maybe some extra factors of L? And the answer is no, because our atom wave function is in there. And that's going to cut everything off at distances much larger than the Bohr radius. And so for the purposes of the integral, there's no L dependence except this L dependence right there. Okay, so in other words, we've correctly got the right L dependence. And now we can make things a little bit easier for ourselves if we recognize we've got two exponential factors that are almost the same. And we can combine them by defining little q to be little k minus big K. So again, little k is for the photon, big K is for the electron. Okay, and so, oh, also, this P sub f is otherwise known as h bar times capital K vector. That's the momentum of the final state. And so now if we clean this up a little bit, this is square root of z cubed over pi Bohr radius cubed L cubed, h bar polarization dotted into final state K vector. And then finally, there's an integral that I'm just going to call I of Q for the moment, where if you look at everything that we factored out, our I of Q is equal to this integral. So as mentioned earlier, this integral doesn't actually scale with L, even though we're integrating over the whole box, because of the exponential that's killing it for large R. Okay, so now we've boiled everything down to doing that one integral. Before we do it, it's a good thing to notice that what does it depend on? It depends on Q, so it depends on the transfer of momentum between the initial and final state. But it really only depends on the magnitude of that, because everything else besides this factor, everything else in the integral is spherically symmetric. And so if I change my direction of Q but keep its magnitude the same, nothing will change. Okay, so another way of saying that is this only depends, once I do the integral, on the magnitude of Q.
I'm sorry, Professor, is that a large K in the previous line?
A large K on the previous line. This one?
Yeah.
Yes, that is a large K.
Thank you.
So it came from here, which in turn came from the final state momentum. Yeah, keeping track of the large Ks and little Ks is kind of painful, but okay. So this only depends on the magnitude of Q, not the direction. Okay, and so what we can do, this is a very common trick, is once you recognize you're trying to do some integral and you notice that, oh, it depends on a vector, but it only depends on the magnitude of the vector, then you get to choose the direction of the vector temporarily to be anything you want at your own convenience, secure in the knowledge that the answer can't depend on your choice. Okay, so we will temporarily choose our q to be along z hat, which means that we're setting it equal to its magnitude times z hat. Okay, once we're done computing the integral, we don't want to do that anymore because we want q to be arbitrary. We want the final state electron, even if we fix the momentum of the initial state photon, we want the final state electron to fly off in any direction it wants to fly off in. Okay, so we will only do this for the purposes of doing the integral. Okay, so let's do that. Now we're going to just write everything in spherical coordinates. So there's a dr r squared. There's a -1 to 1 d cosine theta. There's a 0 to 2 pi d phi. And then there is going to be an e to the minus r. And the crucial thing here is it's e to the minus r times stuff, which is going to be a constant as far as the r integral goes, but it's actually dependent on theta. Okay, so that's our integral we have to do. The easy part is the phi integral. Nothing depends on phi, so that's just going to give us a factor of 2 pi. And then it's hard to know at this point whether you should do the r integral next or the cosine theta integral next. Actually, you can do it either way, but I happen to know that doing the cosine theta integral next would be a good idea. And so let's do that. Okay, so do cosine theta integral next. Okay, and so again, that's not too hard because we're doing an integral cosine theta, and we've got an exponential here involving cosine theta. And so when you do it, you get I of q is minus 2 pi I over q. We still have to do our dr integral, but what's left here is r times e to the minus r z over Bohr radius minus iq. That's from the cosine theta equals 1 limit of integration minus the same thing, except from the cosine theta equals -1 limit of integration. So that's the integral that has to be done. And some of you have learned the hard way that plugging these things into your favorite integral doer software doesn't necessarily guarantee success because some of these things are not too bright. It's actually refreshing and reassuring that human beings are still better at doing integrals in some cases than computers. Okay, but you can actually do this yourself. That it's not that hard. And here's the answer. 8 pi Bohr radius cubed over z cubed 1 plus q squared Bohr radius squared over z squared squared. So maybe just as an aside, since I claimed it wasn't that hard, I should say something about the strategy of doing this. Since you're only integrating over r, you just recognize that both parts of the integral look like this. This is the form that they have. dr times r e to the minus r times some number. Let's call it n, right? And so now, hopefully, your integral software will be able to do that, or you'll be able to look it up. Okay, but even if it can't, you can notice here's a trick for doing an integral like this. This is equal to minus the derivative with respect to n of this integral, which is not too bad. So I take the derivative with respect to n, that pulls down the factor of r, which you see here. And then the minus sign takes care of the minus sign. And so now you just have to do that one. And that one's an elementary integral, integral of an exponential. Okay, so that was an aside. That's sort of how you can get this. You have to do a little bit of combining then because it involves IQ and minus IQ, but it's going to give a real part that you can compute. And so that's the integral. And now finally, we've got the integral. We can plug it into the matrix element. We can take the matrix element and plug it into this formula. And so we are all set. So I'll just summarize what you get here. The differential cross-section is the constants clear out and give you 32, fine structure constant, h bar, the magnitude of k over mass of the electron times omega. Then there's this factor that came from the polarization dot product with the momentum. That gets squared. And then there's finally a Bohr radius cubed over z cubed. This is all from the matrix element. 1 plus q squared, Bohr radius squared over z squared, all to the 4th power in the denominator. Okay, so good things to notice about this. As promised, the dependence on L is gone. That's a good thing. It doesn't matter whether we used a box of length 1 light year or 5 light years. Okay, and in doing that, there was a cancellation between the density of states and the matrix element. They each depended on L separately, but when we multiply them together, that's when they cancel. Okay, and then another thing that we can notice comes from this factor. Okay, and so what is that factor what's that factor trying to tell us? It's trying to tell us that this cross-section is largest when capital K and the polarization are parallel. So let's pause to understand why that should be true. By the way, that also implies that because the polarization is perpendicular to the direction of the wave, that means it's largest when the final state electron momentum is perpendicular to the initial photon momentum. So that always has struck me as a little bit surprising because I'm sending in a photon with some momentum direction. I might expect my electron to go popping out in the same direction, but no, it wants to come out perpendicular. And the direction it does want to come out is the direction of the polarization of the wave. So if we go back to our cartoon of what's going on here, here's our atom with some electron hanging out, and along comes an electric field from our wave that's oscillating up and down like that. That's the polarization direction. Okay, it's a long curly E hat. And so I can go off in any direction I want, my electron can, but it's going to be largest in this direction. So the reason this makes sense is because the electric field is what's pushing this electron out. And so it's natural that it should go out in the same direction the electric field is going, which is perpendicular to the direction the photon is going. Okay, and so it's actually smallest. In fact, it vanishes. Maybe I shouldn't say smallest, I should say 0. It's 0 in the forward direction. There's no chance that the electron will come out the same direction that the photon coming in, just because the electric field is perpendicular to that direction. Okay, any questions on this formula so far? Because basically we've worked out now the formula for the photoelectric effect. And so the rest of today is just looking at a little bit of the details of this formula. Okay, so to understand this a little bit better, let's choose a coordinate system. Notice this coordinate system that we're about to choose is different from the coordinate system we use to evaluate the integral. Where for evaluating the integral, we took little q to be along the z direction, and now we're going to say, no, let's not use that coordinate system. Let's use one where the photon direction, k, is along the z direction. Okay, so k, little k is that. And let's choose our polarization. It has to be perpendicular to the z hat direction. So let's choose it to be x hat. We could easily choose it to be y hat, but x hat's just as good. So let's choose it to be x hat. Okay, and let's write just theta and phi from now on mean the final theta and phi for the direction of the capital K vector. Okay, so it's basically that's going to be theta. And then phi is the rotation around that 0 dotted line. Okay, so now we can evaluate things in this coordinate system. Curly E dot K is K sine theta cosine phi, just plugging in x hat and y hat. And Q squared is little k minus big K squared. That's how we defined it. So this is going to be capital K squared plus little k squared is otherwise known as omega over c. And then there's the cross term from the dot product, which looks like that. Okay, and so now we plug those things into our formula for the differential cross section. This is just evaluating it in a convenient coordinate system. And so we get our constants out front. And more constants, Bohr radius cubed, but I'm grouping it together with capital K because capital K has units of 1 over length, so that Bohr radius times K is dimensionless. Okay, divided by z cubed. And then there's a denominator that involves two numbers, which I'm going to call n1 and n2. And the dependence on the angle is just linear in cosine theta. And then it's to the 4th power. And then there's this factor, which comes from the polarization part. Okay, and so what are the numbers? N1 is just 1 plus Bohr radius squared over z squared, capital K squared plus omega squared over c squared. And the number N2 is 2 Bohr radius squared over z squared, k omega over c. So one reason for writing it like this, where we just isolate all the numbers separately and the angular dependence, we try to make it sort of pop out, is because now we want to integrate this thing to find the total cross section. So to find sigma, which we're going to get by integrating d sigma by d omega with respect to phi and cosine theta. Okay, so now this thing actually depends on phi. We have to be a little bit careful here. There's the dependence on phi. And so that part of the integral is going to be 0 to 2 pi d phi cosine squared theta, cosine squared phi. That integral is just pi. And then the rest of the integral is minus 1 to 1 d cosine theta sine squared theta over n1 minus n2 cosine theta to the fourth. And if your integral calculator doesn't fail you, you'll find out that that is 4/3, 1 over n1 squared minus n2 squared squared. And so in terms of our two numbers, n1 and n2, we now have the total cross-section, right? And so if we know the intensity of the light that we're sending in, then this will give us a number as to how many scattering events we should see. 128 pi fine structure constant h bar over 3 mass of the electron omega, Bohr radius cubed, k cubed over z cubed, n1 squared minus n2 squared, you just plug in those numbers, squared. Okay, so there's our formula we've worked out for the total cross section. But you may remember last time that we were saying that this only should work in the limit of large K, large capital K. And the reason for that is because only in the limit of large capital K is the final state really approximated decently by a plane wave. If K is smaller, then it's going to be perturbed by the nucleus and it won't really be a plane wave at all. So we should be a little bit careful and only look at the limit where capital K is much, much larger than omega over c and much, much larger than z over the Bohr radius. Because those are the two things that we worked out last time it should behave like. Okay, so in that limit, if we go back up to our n1 and n2 formula, so when we had this factor of n1 minus n2 cosine theta to the fourth power, really the n2 is much, much smaller than n1. And so this just works out to be z over k Bohr radius to the 8th power. So where did we get that? We just went back up to here and we said, aha, for large K, this is the only thing that matters, right? And that's got K squared in it, which is how this works out to have K to the 8th power. Okay, now, actually, you can keep the next term expanding in cosine theta, and in the notes that's done, but basically that's the story. Okay, and so now if you plug into d sigma by d omega, things simplify a lot. Okay, and so there's some z's and k's and a's, and the 8 actually cancels with a 3 to give you to the 5th power. Okay, so that's a little bit simpler formula than we had before we took the limit of large K. And notice this is really easy to integrate because now we don't have any crazy denominators. We're just integrating that and that. Okay, and so the total cross section is 128 pi fine structure constant h bar over 3 mass of the electron omega times this factor that goes like the 5th power of 1 over k. Okay, now we can even write this in a slightly neater way by recalling specifically that h bar squared k squared over twice mass of the electron, that's the energy of the final state electron, that's equal to h bar omega plus this factor from the binding energy. But this is is specifically what we're assuming is small. And so really, capital K is approximately square root of 2 me omega over h bar. So we can go ahead and plug that in for K, and then rewrite the other factors like the Bohr radius here and the fine structure constant. We can rewrite those in terms of the binding energy of the electron in its initial state. And so the cross section ends up looking like this. There's a fine structure constant. There's Bohr radius over z squared. And then there's the energy dependence. And the energy dependence is the initial state binding energy in magnitude divided by h bar omega to the 7/2 power. Okay, so where did that come about? That came about because the K here is carrying some powers of omega, but then there's an omega there. And so when you work out how it depends on omega, it's 1 over omega to the 7/2 power. Okay, so the idea is if you're doing an experiment, you send in photons with known energy. The known energy is h bar omega. You measure how often do you get an ejected electron, and it should behave like that energy to the -7/2. So the larger energy you send in, the fewer electrons you should get out. Okay, and so just commenting on this. Oh, so first of all, let's make sure the units work. So I've written this as a dimensionless ratio, so this has no units. And the fine structure constant, you should know, has no units. It's a pure number, about 1 over 137. And then we've got the Bohr radius here. And so this has units of length squared. And so the whole thing has units of area the way it should. Okay, and so this is a fairly famous formula. The key features of it are, first of all, we haven't mentioned it in a while, but you need a minimum energy. That was the delta function. So the energy has to be larger than E bound. Once it's above that energy, it decreases for large energy like energy to the 7/2. That's the h bar omega. And then the ejected electron tends to be along the light polarization direction, which is necessarily perpendicular to the light direction itself. And then the other key thing to remember about this formula is that because we assumed the final state was a plane wave, it's really only good for K fairly large, and so it's wrong for small k. All right, any questions about that, about the photoelectric effect? All right, so if not, as a reminder, we have a midterm on Monday, which covers basically homework set 6, 7, and 8, with the exception of, probably, as you all should have gotten in an email last night, I had a bad typo on the 4th problem of there, so that doesn't count. And so you can ignore that problem for the purposes of studying, except to the extent it overlaps with other problems. Oh, in my email where I talked about the typo, there was a typo in the email just to make things even better. So you'll see that problem again when it's all fixed up. So the midterm information is on the course webpage, and Are there any questions I can answer about that? It's the same room, same everything. Okay, if not, then I will hopefully see you all on Monday.
Thank you. Have a good weekend.
All right,
Thank you.
have a good
Thank
weekend.
you.
Thank you.